Hello everyone and welcome to today. We are announcing our 2025 Student Competition winners. Thank you all so much for attending and joining, and for those of you who missed it, thank you for watching this to find out who our winners are going to be. So without further ado, okay, as I said, we are going through, this is our award ceremony for TecQuipment's 2025 Student Competition. And I just want to start off by saying a big thank you to all the teams and the institutions that entered the TecQuipment competition this year. There were a wide variety of entries using a variety of equipment. We've had entries from our fluid mechanics range and our materials testing and properties range, and the videos submitted were amazing quality. The standard of entries on the whole was high, and when we averaged the scores, there was only 1 point difference that separated our winners and our runners up. So you can tell just by that the high quality and the great caliber that these videos are. Now, I just want to go through videos that did well, because we want to be able to continually give you improvement and feedback. So by providing what videos did well and what videos improvements could do, hopefully it means any other video submissions you give will be even better and make it an even smaller percentage between the winners and the runners up. So, videos that did well. They introduced the equipment and the experiment really clearly, so for us as judges, it made it really easy to understand what was happening in this video. They provided a background as to why the experiment was being performed. So again, us as judges, we're not left questioning or wondering, what is happening in this video? What am I looking at? So by having that clear outline, we can just sit back and really enjoy what is happening in that video. So videos that critically analysed the results that were presented, they showed us what was happening and why, and if there was any errors, what they would do differently, or how they could mitigate this in the future, or if they can't mitigate the errors, why is it important to know this? They also showed and demonstrated using the equipment in an easy to follow step-by-step process. This was really great to see, because us as judges, we all work at TecQuipment. We all know our products, so we understand what we're seeing, what you're doing, and the outcome of what you're going to do. But for when we post these videos, people watching it aren't going to really know. So having a step-by-step process really shows customers your full use of the equipment and how you using it and your outcomes can influence things in the real world. And that relates to the last point, real world situations. So how using our product can influence your studies, but what it would mean in the real world. Because we're all about practical hands-on education. So being able to use our products to learn something, we want your videos to have that same process. And the top videos that did well did just that. So as I said, we'd like to also give feedback for improvement to try and help all the other videos get even better scores to make it even greater videos in the future. So a point to improve, have a clear outline of what the presentation will be about and its purpose. So having a step-by-step or a timeline or just a really clear introduction makes it really easy for us as judges, as I said before, just to sit back and enjoy your video. If we're left guessing or we're not really clear on what the video is about, this is where you will lose points. Potential errors in the work that needs to be addressed. We know in engineering sometimes errors can occur. The best thing to do is problem solve this and understand why. If you do that in the real world, why can't we see it in the video? We want to be able to help you kind of assimilate into the situations that you will be in the future. So telling us these errors will help with this. So methods do allow for higher accuracy to be obtained, but there is still a source of error. So even if a product apparatus or specimen, your experiment has led to a really high accuracy, there are still things going to happen which could be sources of error. So explaining these potentials will really boost your points up to the maximum. So, what we're here for today, the two videos from York College of Pennsylvania and Southampton Solent University, who are battling it out for the crown and winners of TecQuipment Student Competition 2025, are the following two videos. Now we're going to watch both videos and then find out who the winner is.
From York College of Pennsylvania, studying civil engineering. Together, we're excited to present our research on the influence of weir nose geometry on broad-crested weir hydraulics. Water is one of our most vital resources, and managing its flow is critical for both communities and ecosystems. Broad-crested weirs are essential hydraulic structures using dams, spillways, and flood control systems. Broad-crested weirs control water flow to prevent floods, ensure steady water supply for various needs, and protect communities by managing downstream speed and volume. But not all weirs are the same. Small design variations, such as shape of the nose or its radius, can significantly impact how water behaves as it flows over the crest. These differences affect the flow velocity, water levels upstream, and even the efficiency of water discharge. Our experiment focuses on these geometric differences, specifically how varying the nose radius of a broad-crested weir changes the flow characteristics in a controlled channel. To answer our research question, we designed an experiment to study how the nose radius of a broad-crested weir affects the upstream head, flow velocity, and discharge coefficient. We utilized the 2.5-meter flow channel, a hydraulic bench, and 3D printed weirs with different nose radii. In our experiment, we tested 6 different nose radii for the broad-crested weirs: 0, 10, 25, 40, 75, and 100 millimeters. When water flows over a broad-crested weir, fundamental energy and continuity principles govern its behavior. The surface level drops as water accelerates onto the weir crest due to the narrowing flow area. The total head H combines static and velocity heads above the crest, as described by the continuity principle and Bernoulli's equation. Real-world factors like friction, turbulence, and non-uniform flow cause energy losses, which are captured by the discharge coefficient C, which adjusts the theoretical discharge equation to calculate the flow rate Q. We then vary the weir's nose radius and flow rates to achieve different upstream heads, aiming to see how geometric changes impact water flow efficiency. To start our experiment, we connected the hydraulic bench's outflow pipe to the flow channel's inlet pipe, turned on the pump, and adjusted the flow rate to achieve specific targets, recording them with the bench's flow meter. We tested multiple weir shapes, some with no radius, other with nose radii of 10, 25, 40, 75, and 100 millimeters. For each weir, we focused on measuring water depths at specific points under controlled flow conditions. First, we placed the weir into the flume, centering it carefully. This position remained the same for all weirs for consistency. We measured the upstream water depth by using a depth gauge at a fixed spot on the water surface, then calculating the difference between this measurement and the upstream reference height. Next, we used the depth gauge to record reference heights. These measurements, taken at the start, middle, and end of the weir, serve as our baseline for comparing water depths during the experiment. We then measured the water depth at the surface at the start, middle, and end of the weir crest, relative to its corresponding reference height. To ensure reliability, we took 3 measurements at each position and repeated this process for 4 different flow rates. After testing one weir, we replaced it with the next weir shape. We repeated all steps, recording reference heights, adjusting flow rates, and measuring water depths. By keeping our methodology consistent, we ensured reliable comparisons between different weir shapes. The top graph showing upstream total head and depth above the weir crest versus discharge illustrates that the smaller nose radii result in higher head and depth. This translates into the bottom graph, where the discharge coefficient, represented by the slope of the trend lines, increases with larger nose radii, improving hydraulic performance over the weir. This next graph illustrates the relationship between discharge and upstream velocity for different nose radii. Similarly, as expected, the graph shows us that larger nose radii consistently lead to higher upstream velocities for the same discharge. These graphs show how different nose radii on broad-crested weirs impact velocity distribution at different flow rates. Consistent trends appear across all configurations, with minor differences due to the changing nose radius. Overall, our findings confirm that the larger nose radii improve flow by reducing resistance. At low and high flow rates, the no radius weir had a 4.9% and 6.08 higher upstream head difference than the 100 mm radius weir. Upstream velocity for the 100 mm radius weir was 16.4% and 16.1% greater at low and high flows respectively. The discharge coefficient using total head was 8.61% higher for the 100 mm radius weir, aligning with expectations. Larger nose radii improve weir efficiency, reducing resistance and enhancing water management. Slight measurement variations in environmental factors could affect results. In conclusion, larger nose radii enhance hydraulic performance by reducing resistance and increasing upstream velocity.
So that was our top video from York College of Pennsylvania, and they are fighting this video from Southampton Solent University.
Hello everyone, today we'll be taking you through our submission to the TecQuipment Student Competition. I'm Jonathan Hutchins.
And I'm Ian Charlton.
And we are second year undergraduate mechanical engineering students at Southampton Solent University.
We are excited to present our project, which was developed as part of our engineering materials module under the supervision of Dr. Tahan. We'll be answering the question, can we identify unknown materials using mechanical properties in experimental testing? This is important because in industry, safety, and verifying your suppliers are common concerns, and recycling is an ever-growing need.
The TecQuipment that we're using today is the SM1002 benchtop tensile testing machine. On the right side, we have the small course adjustment wheel for setup and a large wheel with a 50:1 gear ratio, which is used during tensile testing. Between the chucks, we've placed a long specimen for use with the optional extensometer, so we can calculate the Young's modulus. To find the ultimate tensile strength of our materials, we need to use the short samples without the extensometer fitted. Data is measured by the load sensor and displayed on the digital load meter. The extensometer dial gauge is connected to VDAS software, where we input the sample dimensions and record the data from both the extensometer and load cell. This allows us to calculate the stress and strain.
This is how we'll approach the research question. We'll start with pre-test measurements before moving on to the testing. Then we'll analyze the results and use the results to try and identify the materials. Finally, we'll use several methods to verify our findings. To help narrow down the possible materials in the database, we calculated the density of each sample based on volumes and the masses. By using the density formula, we were able to identify a key physical property that supports material identification.
Across our three samples, the behavior called necking is exhibited. This is where the material plastically deforms beyond the maximum tensile strength before fracture, causing a reduction in cross-sectional area. In the stress strain graph, this is where the curve begins to fall off from the peak.
Initially, we struggled to measure the elongation and reduction in cross-sectional area of fractured samples with a caliper, as we need to reassemble them. To rectify this, we used two alternative methods.
The first method was image analysis to calculate the reduction in area. We used the images captured during tensile testing and, using a no measurement, captured the pixels per millimeter and applied that scale to the unknown measurement. This was more accurate.
The second method was using analog gauges. The gauges are pictured on the right, and it was found that the elongation gauge was more precise for measuring elongation. However, image analysis was more accurate for measuring reduction in cross-sectional area.
We measured the tensile strength of short samples, and in our tests we observed variation in results. Some contributing factors such as machine accuracy, material defects, and slight misalignment during clamping added to the variation.
An extensometer, along with the longer samples which are pictured on the right, were put into the tensile testing machine, which was then brought to a set force to ensure we stay within the elastic region, the data for which was used to calculate the Young's modulus.
We compiled our data comprising of the material density, Young's modulus, elongation percentage, and ultimate tensile strength in this table. We used the ANSYS Grant Level 3 material database of metals to identify our sample materials by applying the limits. In the case of material A, we found it must be a variant of carbon steel or stainless steel. Material B and C, we reached a much more conclusive selection of brass and aluminium.
In material A, we observed a classic cup and cone fracture, which is a clear indicator of ductile failure.
A faint cup and cone shape is present, but it's much less pronounced than in material A. The tooth-like features around the edge suggest a mix of ductile and brittle behavior. This aligns with the properties of brass, which has moderate ductility, but can fracture more abruptly under certain conditions.
The break shows a distinct angled shear plane and relatively clean surface, with little necking. This suggests a relatively brittle failure under shear. Even though aluminium is generally considered ductile, the behavior can be influenced by work hardening or surface flaws in the sample.
As an extra step, we tested the magnetic properties of each sample to help narrow down the material types. This was especially useful in distinguishing between carbon steel, which is magnetic, and austenitic stainless steel, which is generally non-magnetic.
We can conclude that the method used was successful in identifying materials.
However, other testing methods are required for higher accuracy on the specifics of material processing and grades.
Thank you for your time and consideration. I've been Ian.
And I've been Jonathan.
So, those were our two videos fighting for the crown and the title of TecQuipment's 2025 Student Competition. As I said, from York College, Pennsylvania and Southampton Solvent University. And I'm sure we're all excited to find out who our winners are. Now, as I said earlier, we had some really high caliber videos from all our entrants, so I just want to give a round of applause to those who also submitted. Now, between those two top videos, there was only 1% difference between them, which is amazing, and we are so grateful to have you submitted these videos. Now, the moment we're all here for and the moment you have been waiting for, the winners of TecQuipment's 2025 Student Competition, who will walk away with £1,150 certificates and a custom-made trophy are... It is Southampton Solvent University Team 1 for identifying unknown materials using mechanical properties and experimental testing. Jonathan and Ian, your video was great, and as I said, that 1% difference really worked in your favour, as you are now TecQuipment's 2025 winners. Congratulations to all. And I also just want to say congratulations to everyone who did enter our competition. Your videos and your work are amazing, and it really helps to show how you can take practical engineering education, use it, and how it can be used in the real world. So I've been Zoe, and thank you for taking the time to watch this video today. Enjoy, and we hope to see you soon.